Okay. Let's blow it up just a little bit. That looks good. Okay. I'm gonna go down, go down to the questions. Excuse me. Let's see, that's data. PreLab, here we go. All right. So I didn't leave myself much room, did I? PreLabs. I'll put them down here. They'll get recorded. Let's see. Yeah, they'll be recorded. So PreLab number 1, by the way, no, I'll wait on that. We'll just do the PreLabs first. Okay, PreLab number 1, and it's got parts 1 and 2. So the first activity is to calculate the amount of sodium chloride needed to prepare 50 milliliters of 0.9% sodium chloride solution. If we need 0.9% sodium chloride, what does that mean? Remember, percent is a dimensionless number. Unless you know what it's telling you, it's parts per 100. In this application, it's mass per volume. So it'll be 0.9% sodium chloride, or 0.9 grams per 100 milliliters. That's what that means. Now that we know what that means, if you have to prepare 50 milliliters of it, then since milliliters is in the denominator, we just multiply 50 milliliters times that. Okay? So what would that be? Well, 50 divided by 100 is a half, right? So a half of 0.9 is 0.45 grams of sodium chloride in 50 milliliters. Okay. Part 2 wants us to prepare 20% sodium chloride. All right. Same logic here. We have 20 grams per 100 milliliters times 50 milliliters. All right, milliliters cancel. Take a half of 20, and that's 10 grams of sodium chloride. Okay. It's pretty simple. All right, that was number 1. Let's look at number 2. Two has several parts. Explain the following terms. Isotonic. Have you had biology or anatomy and physiology or anything? So you've never been introduced to the idea of tonicity? No. Okay. Well, let's go to, here it is. Beginning on the first page, it's talking about osmosis. When we're discussing tonicity, usually in a biological sense. In other words, the cell has a membrane, and the membrane allows certain things to pass through it. And the membrane is really more complicated. It's more complex and controlling than a simple membrane. But we have to treat it that way for discussion purposes. So an isotonic solution is one in which the concentration of solute inside the cell is the same as outside the cell, because the membrane will transfer water across the membrane, but it transfers based upon the concentration gradient. What I mean by that is, if we have a membrane here, we got water on both sides, and this is pure water, but this is a solution with some dissolved solid, like let's just make something up, sodium chloride. It's got some sodium chloride on this side. In this situation, which way is the water going to move? Sodium chloride can't cross the membrane. So in order for, what happens is the water molecules are trying to pass that membrane from both sides. But since sodium chloride is on this side and it has an attraction for water, it holds it back. So it's not as active in that direction. So the water tends to, the net movement of water is this way toward the more concentrated solution. Okay. If this is inside the cell and this is outside, then this solution out here is said to be hypotonic. It's less concentrated in the solute than inside the cell. And when it's hypotonic outside, water tends to move inside. If we switch the roles, if we put the cell on this side and the outside here, then the movement of water would be out of the cell. Okay? So in the isotonic situation, concentration of solute is identical on both sides. All right. Let's see. Well, there it is, number 2. I mentioned hypotonic already. A hypotonic solution, 2. A hypotonic solution is one in which the solute concentration is lower than inside the cell. Hypo meaning underneath or less than. Like hypodermic, like under the skin, less than. And then hypertonic should be the next one, I think it is. Yeah, hypertonic is a solution that is higher concentration of solute outside the cell than inside the cell. All right. Number 3. What's the function of dialysis tubing? Dialysis. Do you have any relatives that have had kidney failure? Okay. Before a kidney transplant can take place, since they're so in short supply, what the patient has to do is undergo dialysis. And what dialysis does is it takes the blood and runs it through, pumps it through a dialysis tubing, and surrounding the tubing is a solution that is deficient in the toxins that are contained in the blood that the kidneys would normally excrete. And by doing that, dialysis tubing allows those toxins to cross the membrane into the dialysate outside the tubing, and then the blood is delivered back to the patient, essentially clean of those toxins. Well, those toxins are all small molecules, like urea. Yeah, urea is a big one. So the dialysis tubing's purpose, its function, is to allow small toxic molecules to cross its membrane and clean the solution that passes through it. Now let me see if yeah. Now there's a contrast between the semi-permeable membrane and there are two words for this, either differentially permeable or selectively permeable. These two are synonymous. The semi-permeable membrane is one that only allows water to cross it, or anything smaller, like gas molecules will go through those membranes. But for our purposes, we're focused on water crosses the membrane and nothing else. Differentially permeable membrane, they have larger pores, and they allow differentiating between the sizes of molecules. So you can have different grades of this membrane with different pore sizes, and they get bigger and bigger. And the one we're going to use today, this is dialysis tubing, this differentially permeable or selectively permeable. And it's most often used in dialysis of patients with kidney failure. The process that we're describing here is called hemodialysis. Oops. It's not a Y, it's an I. Dialysis, hemodialysis, in which the blood is pumped through the tubing, and then the toxins cross the membrane into the external solution, the dialysate. Okay. What's the purpose of Benedict's solution? Benedict's solution. Benedict's solution here on this table is the blue solution. Benedict's solution detects what we call reducing sugars. Non-reducing sugars won't be detected. Now, what do we mean by reducing sugar? Well, sugars have lots of hydroxyls sticking off of them. Right? They'll have a carbon backbone like this. 1, 2, 3, 4, 5, 6. Right? For glucose and fructose and a lot of the sugars are hexoses. They have 6 carbons, and they'll have hydroxyls off of them. Oops, there. And at the end, they're like that. The rest of these are hydrogens. Well, this is the reducing part. This, what's called a carbonyl group, will reduce the Benedict's solution and change colors. So it's detected. But what these sugars do is one end grabs its own tail, and they make a ring structure. Depending on the ring structure, if the ring structure is able to open up and close at will, then this reducing part is still available for detection. But if it's somewhere along here and it closes up and it won't open again, then it's a non-reducing sugar and it's not detected. So in our case, we're using glucose, right? The same sugar that pumps through your blood system and gives diabetics problems. And that is a reducing sugar. So Benedict's will detect reducing sugar, in our case, glucose. How about iodine? What's the purpose of iodine? As an indicator, the iodine test. It detects starches, right? It'll turn a very dark purple in the presence of starch. Now, the chemistry behind it is rather complex, so we're not going to bore you with that. That's what these tables are for. Right? This is going to be the iodine test. This is going to be the Benedict's test for our dialysis part of the experiment. And then over here, the osmosis test, we're just going to measure the physical characteristics of a potato core. Okay. All right, that was number. Well, actually, it was 4 and 5 was Benedict's here. 4 and 5. Iodine detects starches. So why do we need those tests? Because when we put we're going to mix up a starch solution and a sugar solution together and put it inside a dialysis tubing and seal it off and then stick it in a larger test tube with distilled water. And then we're going to test the solution outside the dialysis tubing, which is the dialysate. And test one for reducing sugar and then do an iodine test on it also and see which one passes through the membrane. Now, if everything works as it should, the simple sugar should pass through the membrane, but the starch should not. It's too big. It won't go through the holes. Those are our expectations. Okay. So let's see. I've covered some of this already, right? We already know about solutions, difference between semi-permeable and differentially permeable, isotonic, hypotonic, hypertonic, what's dialysis, what's hemodialysis. The dialysate is the solution outside the tubing that accumulates the toxins. Let's see. We're going to make, the reason we did those calculations with the different sodium chloride solutions is pure water is hypotonic. Like 20% sodium chloride is hypertonic and 0.9% is isotonic. So this is hypertonic, isotonic, hypotonic. And here's the procedure. So I guess that's all we need to know. All right. So let me erase this. And we'll just leave the data tables up here. Okay. So it looks like we're partners again. Did you get copies of these? Okay. Let me see if this cooled down. I ran off and left my, I had prepared glucose and starch solutions, and they were in my refrigerator in the lab, and I forgot to put them in the kit. So I had to quit and make them up this morning from the current stock. So you want to go there or here? Let's go here since we'll be closer to the stuff. Okay. So I'm going to assist. And I'll let you direct the procedures. So I would look at the procedure. I would try to work with the data. So the first thing you have to do is make up those solutions. Turn this on. And you're going to need sodium chloride, salt, and got your bearings yet? No. Okay. You have to make up 3 solutions. Actually, 1 solution is pure distilled water. I don't know if solutions. One's just water. Mark it on the side. So you can see it.
The 20%, the ones that 25%.
Yes. Then you have to calculate how much sodium chloride to give you. Now, what's the volume that it wants? 25 milliliters. The pre-lab question we did was for 50 milliliters. So if you only need 25 milliliters, you just need half as much sodium chloride, don't you? So it was what, 0.45 for the 0.9? So that is 0.225. Sodium chloride. Yep. Hey, that's coming up. That's what we're doing right now. Making the solutions. Might be easier. So I would set my beaker in there. Zero it out. That's twice as much as you need. Do what you- 0.45. Let's go to 0.45. Okay. Now instead of 25 mils, with 50 mils. Just make a solution like we did with that question. It's going to be the same concentration. Let's see, heat it up. What's your bucket?
Oh, don't remember.
Do you remember?
Nope.
I was you need 50 milliliters, right? We're going to do 25, now we're going to do 50. No. Make it 25 minutes. Or you're going to go all the way to 50.
I thought this one was the 10 one.
Yeah, you're going to need 5 grams, is it?
Supposed to be, but we went ahead and done.
Yeah, you can go to 50 if you want. So that'd be 10 grams, was it?
Yeah.
Okay. That's perfectly all right with me.
I put too much in it.
Oh, because it was wet. Okay. Yeah, go ahead, though. Get 50 milliliters in that graduated cylinder right there. Is that? So. Get there. What's the solubility? So, right. Maybe saturated. Since these are relative formulas, this is. It's, well, this is high concentration. All right, so what's next? Hit a cord again. Let me get some paper towels. Okay. We're going to get the mass of the core and the length of the core before we put it in the subfloor. So it just needs to be towel dry. And I would rather than put it right on the pan, I would just zero it out. One button. Okay, so we need 3/4. In my punch. How long does it take? Millimeters? Oh, 2 to 3 millimeters. How long? 40 milliliters. Get you. Yep. Do them all exactly, and that makes the data easier to record. Now we need to, and that would be exact, so we have to decide. Let's see, what's the order we're gonna have? Cylinder 1 is 20%. This. Cylinder 2 is 0.9. Cylinder 3 is 1, 2, 3. 1, 2, 3. I just wait. Each time you wait one, put it in solution.
Zero point 515.
515. 5. Okay. Yep.
Zero point 507.
But we have to note the texture too. What's the texture of each one of them at this point? Are they, I think we're more interested in, are they rigid or limp? They're fairly rigid, aren't they?
0.519.
Okay. Now they sit in that solution for what, 45 minutes, I believe. Is that right? Yeah, timer. Set your timer. 5 minutes. So load it to the 5. It's 4. It's less dense than the solution since we have salt. It's like trying to swim in a swimming pool with fresh water, or swimming in a lake, or versus swimming in the ocean or swimming in the Dead Sea. They say in the Dead Sea, right, you're like mostly out, you're way out of the water because it's so tense. Your buoyancy is great. But in fresh water, you're going to sink like. Okay, so that we just let those sit 45 minutes. While they're doing that, we'll get ready for the other next experiment. We'll come back to that. Okay, what's next? Got to do our tests. We had negative control, positive control. Here it is. Because the Benedict's test has to be heated for the reaction to go. I mean, it'll happen at room temperature, but it'll take forever. Iodine happens just like that. But Benedict's results short. 60. Does it say what temperature or is it what board? 60. I think it's boiling because doesn't the method call for a boiling tube? The boiling tube. Yeah.
Right, so,
I got this extra. This one starts. Yeah. Okay, what's next? We're gonna do this. These two.
between 150 this to fill it full with distilled water. Press the tube into
This one. With distilled water. And it's crap about it. Yeah, it's just a guess. It's not even in the door. Ooh, that hurt.
yes.
It's coming up a little.
I soaked 200 millimeter piece of dialysis.
Okay, it's right over here. It's several of them. Really delicate. What does it want you to do? I don't know. What it is. There you go. That one. What's your own?
Sharon Rod with the reproduction.
Get it started. Yeah, you just kind of back and forth to think trash bags. Trying to get those open.
Storage solution is free for the
So starch, they want starch first. I don't have any squeeze bottles. keeps closing up on you. That's why they say squeeze ball. Then you can stick the tube in. Hey, what? Yes. Here. Yeah, we talk.
Using a 2% glucose solution for the, systemic to within 25 milligrams of its.
Now we have to close it off. So you have two choices. You can use the clamp or you tie this way. You got two different sizes. It's the bigger one, I think. Yeah, fold over the top. See if I can do it. It's a perfect water.
Eight drops of distilled water and 4 drops of meat.
Oh, didn't say submerge this in the water. Say
Ready?
undisturbed. Undisturbed. So now we're going to do our Benedict test, our controls. Yeah, we're going to have the negative control, positive control. Negative control is water.
Add 8 drops of distilled water and 4 drops of beauty. Right.
Distilled water. So this is negative. So we need glucose and distilled water. Negative control. Benedict's. Here we go. This is in a drop box. Should be off the street. Observations, I think. Color before we heat, right? Isn't that what's next? Okay, what's the color before you heat?
Blue.
For both of them, right?
Yeah.
Okay. Now, how long do you heat them?
For 3 minutes.
Okay, is the water hot enough? I think it looks like it's starting to gas off. It's not boiling. Okay. Do we just wait for it or is there something else?
It just says to observe and report your data sheet, the solution of the colors.
Okay. All right. Ooh, it's already started. Positive control of the orange. Let me go some more because it might get darker. Another 2 minutes. Fix this. That's starch. Starch is a polymer of glucose subunits. And the amylase in your saliva breaks those glucose molecules off of the starch. You start chopping it off. Once you get those glucose molecules in there, you get the sweet. Salt. So that's something to add to it. Salt. Flavor. What? Brown. It was orange at first. Okay. So the negative control is still blue, right?
Yeah,
This one turned brown. Okay. Oh, so what does that mean? That means the negative control, sugar's absent. And the positive control, sugar's present. A little too much salt. Okay, what's next?
it's sweet to take out of the solution, out of the water, and turn it off, but keep them for reference instead of something.
Okay. Well, we're gonna need it again. Big turn. Now let's start to boil. We need another beat. Set it in. Here we go.
Prepare iodine test controls, labeled 2012-575, test shipping, negative iodine control. get a drop or drops.
Okay. So here's iodine. This doesn't have the drops. Supposed to have a before and after. No, it's not a before and after, it's just color. Okay, negative control. It's kind of a, what's that? Women are better at both.
G.
And that's this one, negative control. Dark orange. Okay. And that's starch is absent.
This is the same. It's the same color.
Did you put starch in it?
Yeah.
Just oh, that's glucose.
Oh,
Here's the starch. Get your work done.
dark.
Say hello. I think it's the starch solution I made up. It takes a long time to get starch in the solution. I think it just, it says, what, 0.25%. But the solution is probably, you can still see some of the bottom. That's why I'm bringing it already prepared from that. Okay. So that went kind of, I see a little blue. And green, orange and blue, is that green? I almost couldn't see. Are you looking it up? Okay, it looks green. Okay. What's next?
Reheat the water to boiling, water bath. To test the dialysate, I say drops of dialysate in lane 12/575. And then we test tube, add 4 drops of vinegar.
That should have happened. We should have put this in there right away. You didn't tell us to, did you? This is supposed to be. Yeah, I'm not sure how long it's supposed to stay, so I'm just gonna put the stopwatch. Look, you look at my map and see if I made any notes. Okay, not in the procedure, but above the procedure it says, dialysis tubing, then place the dialysis tubing in the test tube containing distilled water after 20 minutes. Test the solution. So we gotta go 20 minutes. We should have said that in the procedure. Here it is. Let the dialysis tubing remain undisturbed for 20 minutes. But it doesn't say, put it in the solution. That's that problem. Undisturbed for 20 minutes in. I'll have to make that correction for future.
Where they come to solution backward. It's hard to.
How we do it on that's something. So that means its density increased. Yes. Actually, based on a theory, this is hypertonic, so water should be out. Decrease the mass. So it's decreasing the mass by removing water. And the solids that are in the core are usually denser than water. So we're increasing the density of the core by removing water.
Still, water about the observe. Record the solution color, compare the color. The colors that are positive and negative control factor.
So that's what we do once this is finished, right? You have to leave this in here. So
Test the dialysate surrounding the dialysis tube with iodine solution plus 8 drops of dialysate. 12/75 milliliter test tube and add 4 drops of iodine solution. Mix the solution observe the color. Test solution inside the dialysis stream process and drops are related to the opening of the dialysis to reach the solutions and observe them.
So we've got places for dialysate, which is the solution around the tubing and inside the tubing. We've got places for that data for both tests. So which one do we put in a tube? We draw some out, put it in here, go to that. For both inside and outside. And then the iodine test outside once. Just put iodine in the tube. So,
I don't understand thoughts enough to understand what that's saying.
okay. Let's see what's next. Step 19 is where we start. Yeah. Step 19 is where we start testing this stuff. To test the dialysate, place 8 drops of the dialysate. So we just grab one of these and reach down in here and get some of that solution.
Well, on number 18,
Uh-huh.
it says it's talking about those solutions. Says taper steps 22. That's the part touching grid.
Solutions from reference. Oh, yeah, that's the iodine test. So 21 and 22 is where we're doing the iodine. 19 and 20 is where you do the benefits. Yeah. So we have to wait. Or this one, Jim comes first. Okay. About 14 minutes left. This one, how about that? So we'll probably get to this one first. These are our comparison. This is honestly this is our number. That's fine. I think that's the third combination. Primaries. Look at that. What colors make green? Yellow. Okay, so close. Orange instead of yellow, purple instead of blue. So we shifted the two, both of them this way. That makes sense. So we're going to end up in green.
Everything like that. We don't need
Mm-hmm. No, those are for comparison. These are for benefits comparison. These. I'll settle down. Mercy. Plus, in Louisiana, I had my garden on my boss's property. He had 111 acres. And fenced in area for the garden. Got 60 head of cattle on 30 acre field. So when we needed organic matter for the garden, we did his tractor and pull a flatbed trailer and pick up cow pies. Bring them back to the garden, dump them in the corner, let the rain wash the salt out of it. Then we go throw them on the garden. So, well, one time, actually, the first time I wasn't married to her yet, or my fiance up there. They always with the garden. She wanted to see the cows and all that stuff. We planted 99 tomato plants. I almost cured her of going to the garden. Well, there was a lot of candy that year.
It's beside my old uncle's house, but now I'm safe sister lives in it. Their neighbor, they have like a big garden like, out back and like they have an apple tree in the front yard and like I don't like a greenhouse, I think is what it's called. And he would come over and plant cucumber plants and let them grow up the fence and all his even growing up.
Yeah. That's good use. We had, we put, loofahs. We grew loofahs on our fence line. And on the fence, and we built a teepee also for snow peas. Oh, good. But the weather down there did not like Brussels sprouts. I couldn't grow Brussels sprouts. They come up as soon as they started flowering, they just pop like that. Instead of making nice little tight cabbages. But I could grow corn, tomatoes,
black eyed peas, bell peppers, eggplant, okra. Okra loves hot weather. But when you go in to pick okra, you're gonna wear long sleeves. Because those spiky things on there will eat you up. And the other thing is, fire ants love okra. So you'll get in there and start picking them, and there come the fire ants. They build their nests around the okra. So by that time, the chemical heptachlor, which is very effective at killing ants, have been outlawed. But my boss still had some in storage. So we throw some heptachlor out there and just knock on the head. Watermelon, cantaloupe, good cantaloupe. You got green beans, pole beans. We got blue lakes and pole beans. Blue lakes are the ones that stay round, and the pole beans are the ones that are flat, have the seeds in them. Those are good. Cabbage. When we pick cabbage, we harvested cabbage, we pull the outer leaves off, throw them over the fence, and the cattle run like a bunch of puppy dogs. And we had cauliflower. You have to, when the cauliflower starts to make the head, and pull the leaves up and tie them off. Otherwise, the sun will turn green. Keep white leaves. We had trouble with the deer. They knew when it was harvest time. We come in and clean out our black eyed peas. And the other thing, it's very irritating. A deer will go through a watermelon patch. They'll stomp 3 or 4 watermelon and only eat one of them. They're looking for the one that they like. That's the sweetest.
Yeah.
And so we tried everything. We hang bags of hair. We have scarecrows. We have electrified fence. I was in the garden one day working, and I heard off in the distance, heard some dogs barking, chasing something. It got closer and closer and closer. Before I saw the dogs, out of the woods came this deer. They were chasing a deer. And he came running up to the fence, our garden fence, just one leaf over one side, ran across the garden, over the other side, no go. I was like, so much for electric fence. They want to, So, planet X. Okay. Now what do? We pull those out, right? I think we need some. Get some tweezers. Forceps. Proper. Yeah. This way you can pluck them out and put them on the paper towel. Just towel dry them so that we're not weighing water. Let's see which one. That's first on the list. It will be that one. Yeah. So what do you say the texture?
Limp.
Yeah.
Flaccid. Flexible.
0.426.
0.426. Oh, and we also need a length. Measure the length.
Three point six.
What?
3.6.
3.6 or 36?
36.
Yeah, because it started out at 40.
I was thinking like inches.
Okay, that's good. Now we'll go to the 0.9%.
Oh. This one's still hard.
It's still rigid?
Yeah.
Okay.
Point 51.
0.51. Okay, and we need a length.
$39.
Okay.
Very hard still.
I'm sorry?
Very hard. Still
Is it harder than before?
feels it is.
Okay.
And this is 0.56.
0.56.
Yep. I assume this wasn't perfect,
What is it?
a perfect cut because it looks like it grew.
Yeah, that's fine.
Okay.
How big is it?
That's 41.
41. Okay. Actually, that's what we expect, right? Because water, which way is it going to move? Into the cells and make it. That made it more rigid and it made it longer. And it made it heavier too. Okay, now we go to the next ones. Let's see.
We've got, yeah, we're past 20 minutes. Yep, couple of beakers. Big ones. Yeah. Then it is. Or do we have to go backwards?
That's the solution inside the Benedict.
Yeah. Solution inside the tubing. We can get outside the tubing too. Yeah. We're gonna do outside and inside.
Okay.
So this is gonna be. Sit outside. Yeah. This is the dialysis. Handcuffs.
Okay.
Yeah. Before we heat, it's still blue, right? Or,
And just sit it in there.
yep. Yep. Then we'll watch to see what happens. 3 minutes, isn't it? Okay, we're at this step right here. Size. Inside, we know as glucose. Outside, it may reaction. It's just taking longer. I think because the concentration is lower. Yeah, if you would, let's go with it. So, it's longer.
Give it there.
We didn't do, we didn't do a control with varying levels of glucose. All we did was the one. It's going to look like that. But what we've got here is a lower concentration. What it's doing. It's gradually.
The green sheet.
So inside, and
like a lucky looking light brown color and then a red orange.
Okay, so inside is kind of a orange. The inside is orange. So when we did the control here, this was full strength. This one was diluted about halfway with the other one. So that makes sense. Brown to orange. How about the dialysate? What does it look like? Kind of a
A light brown.
light brown? Okay. So the important part is what can we conclude? The dialysate has sugar in it? Present? And the inside definitely has present. Okay. So the next one we do is starch. Oh, we still have to do that. Yes. Yeah. These solutions.
Oh, so this one goes in.
Yeah, now, this one is the, see, dialysis. Sorry. This one.
Did they do the same thing?
Was this from the inside or outside? This was outside, right? That's the dial say, yeah. It should be the same color, so. No. Inside should still have some starch here. So they are helps. This one.
Yes. They both have teachers.
Inside the two. That's outside. Should have no starch. No starch. Inside should show us a little starch. That's it. Very big. Say outside should be the point of starch. Orange dialysate could be no starch. Inside, we're not sure yet. Because it's still reacting, and I don't. We didn't mix it up.
Then
No, we can't fudge it. We're saying inside is still dark orange, which means there's no starch. So explanation.
possible dilution below detectable limit. That's what I would say.